So what we're going to do today is, this really follows on from last week's lecture. And so we're going to move on. Last week we were talking about linear models and how we can include lots of predictors in them and all that sort of thing. And this week we'll have, we'll kind of move that on a bit to look at how the models are kind of specified and how we can use them. And then we're going to go back to my favourite subject of bias and have a look at how we can assess whether the models that we fit are actually any good. So we kind of touched on this a bit at the end of last week's lecture because we talked about F and R squared and their sort of measures of fit, broadly speaking. But we're going to go into a whole other world of pain when it comes to model fit in this lecture. Which, just randomly, for some reason that has reminded me, class test happens sometime in the week after next week's lecture. So if your practical class is on a Thursday, your test, exercise, it's not a test, it's an exercise. Your exercise will be next Thursday. So it will be sometime in that week, because people are getting a bit confused about when it is. I've posted something on the forum, but I thought I ought to mention it. Anyway, sorry. So regression, or linear models. We had a look last week at an example where we were trying to predict album sales from how much advertising a record company had spent, or how much money they'd spent on advertising that product. And we had a look at, well, this would be like a simple linear model. And, you know, it shows a straight line. And we talked about how when we have one predictor, we get a line. And then we kind of extended the model a bit. And we added in a second predictor, which was how many times the record company managed to get the record played on radio. And we saw that if you add another predictor in, then rather than a regression line, you get a regression plane. So it all becomes a bit three-dimensional. And we also talked about you could add in even more predictors if you like, but it becomes quite difficult to visualize unless you're on acid. So you are on acid, aren't you? Yeah, so I don't have any graphs for that, but you know, you can do it. And the equation, you know, it just kind of extends, la 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 la. So moving on from this, we're going to have a look at actually how. So you know, we've looked at the pretty pictures. We're now going to have a look at how we actually use the model. So it's the same example. We're just looking at trying to predict how many how many albums we can sell based on how much money we spend advertising it, how many times we get it played on the radio. So hopefully what you would have done in your practical class last week is done a bit of this on SPSS. So gone through some examples, and we talked a bit about estimation. I didn't go into detail about that because it's complicated and we don't really need to know it. But we have these things called parameters that define the model. So these are these betas here, and they get estimated, and SPSS produces this table that tells us the estimates. So we're going to focus a bit for the time being on what these betas represent. We're also, I'm going to come on to this a bit later, you'll notice that you can build up models systematically. So in this case, what I've done is I've put in advertising budget first, I've estimated the parameters, seen what's going on, and then in sort of a second model, I've added in radio, the amount the record got played on radio. So although I don't want to get sidetracked into that just now, that's why the table looks a bit complicated. But we just want to focus on this bottom bit here, which is the model that has it's got our beta 0, or our constant in it. It's got advertising budget as a predictor. It's got plays on radio as a predictor. So these things in this column here are what I keep going on about, these parameter estimates. So these basically tell us something about the relationship between these predictor variables and the thing we're trying to predict, record sales. So we're going to start off by having a look in a bit more detail about how we interpret them. And yeah, it's reasonably straightforward, actually. The other thing worth noting is I mentioned last week that once we've estimated these parameters, we can test whether they're different from 0. And you may remember I was talking about if a beta is 0, then that's like a flat line or a completely flat plane. So what we can do is test whether the beta is significantly different from 0. And if it's significantly different from 0, that means it's not flat. It's, you know, it's going at an angle or dipping down or something. And this t-test at the end is that test. So the t-test tests whether this value here is significantly different from 0. And you get the significance at the end. So the basic idea is if this significance value is less than 0.05, you know, if you want to be that sort of black and white about it, if it's less than 0.05, then we assume that these are significant predictors of album sales. Because it means the slope, the slope or the relationship is different from 0. It's, and if it's different from 0, that 0 represents sort of no effect at all. So how do we use the betas? Well, we use the betas to actually construct a model. This is the worst slide of the lecture, I think. So we saw last week we can build up a model, and if we've got multiple predictors, we generally denote them with x's, but you can also replace them with variable names. So this is what I've done below. So x1 becomes adverts, that's the advertising budget, and x2 becomes plays, which is just the plays on radio. So what that table in SPSS is giving us is the values of these betas. So we can just plug them in from the table that I just showed you. So for example, if I go backwards, our constant, our beta 0 was 41,123. I don't know why I didn't keep the numbers a bit simpler, but anyway. And I've rounded off, but that's the value we get here. So we're just literally taking the numbers out of the SPSS table and plugging them in to construct this model. Similarly, beta 1, that was the parameter estimate for the relationship between advertising and album sales. So we can replace beta 1 with the value out of the SPSS table. And similarly, with plays on radio, we can take beta 2 out of the SPSS table, and that value was 3,589. Now, you might think, why would we do that? It's bad enough that we have to look at equations. Why do we want to make them worse by putting numbers into them? It's because it allows us to make predictions beyond our data. So, for example, if you were working for a record company and you wanted to know how many sales you could expect to get based on the amount of advertising you had in your budget, the amount of money you had, and how many times you thought you could get it played on radio, you can plug these numbers into the equation and get an answer. And that answer, might be useful to you, potentially. So, for example, if we had £1 million to spend on advertising, all we could do is replace this predictor variable, adverts, with the value of 1 million. So that's what I've done down here. And if we think we'll get it played 15 times on radio, then we can replace the variable plays with the value 15, which is all I've done down there. And basically, when you work all of that out, it gives you an answer. So how many sales will you get? Well, if you spend £1 million on advertising and you get the record played 15 times on the radio per week, then you can expect basically 182,000 sales, rounding off a bit. So there's an interesting point here, which is, bear in mind, from the previous table, we know that advertising budget is a significant predictor. So, it has a non-zero relationship. And we know that plays on radio is a significant predictor. In other words, it has a non-zero relationship. But do you think, for example, spending £1 million on advertising, if you spent £1 million on advertising, do you think 182,000 sales is a good return on that investment? No, it's rubbish. You'd basically be this would be like what you'd get if you were trying to sell Robbie Williams records or something. You'd literally be paying people to buy the record. Sorry, is that a bit mean? I'm sure he's a lovely man. That's useful information in a way, because it totally is. So if I was an executive working for a record company, which I often am in my sleepy, dreamy time, I would be sitting there thinking, well, don't spend the money on advertising. We may be better off focusing on trying to get it played on radio, because perhaps that's going to give us a better return. But the point is, you can pick apart interesting things, like don't waste your money, don't waste your £1 million on advertising, because it's not going to increase your sales enough to kind of give you enough money back to cover that cost. So that's why we use these parameter estimates, we construct models, and we start making predictions. It gives us useful information. It's used in business all the time, as well as psychology. So how do you interpret these beta values? Well, the parameter estimate, the beta, it's literally the change in the outcome that's associated with a unit change in the predictor. The word unit in there always potentially confuses people. All that is referring to is the fact that different predictors are measured in different units. So advertising is measured in pounds, plays on radio is measured in number of times per week. So in order to make a sort of general statement, it's just, if our predictor changes by a unit, then our outcome will change by a unit. So in other words, if we spend an extra £1 on advertising, how many more albums will we sell? We can also, we'll look at both of these, we can also standardize these parameters, and that can be a useful thing to do because it gets rid of this whole issue of units. So what a standardized beta value gives us is it's the same thing. It's sort of the relationship between the predictor and the outcome, but it's expressed, it's a bit like a z-score. It's expressed in standard deviation units. So all that means is that we can compare these across different variables. It doesn't matter if one's measured in pounds and one's measured in number of times per week. This standardized beta is the same units of measurement for both of them. It's both are expressed as standard deviations. So standardized betas are quite often more useful in a way because you can compare the strength of relationship across predictors measured in different ways. So let's look at a concrete example. So for our normal beta, so our unstandardized one, for advertising budget, we got a beta of 0.087. So what this means is if we spend an extra £1 on advertising, if our advertising increases by £1, record sales will increase by 0.087 units. So in other words, for every £1 we spend on advertising, we'll sell an extra 0.087 of an album. In other words, not a lot at all. In fact, I think if you sort of flip that on its head and you work out how much you would need to spend to sell one album, it works out about £11.50 or something like that. So, that tells us something interesting because although advertising budget is, a significant predictor, like I said, its sort of practical utility is zero. You'd never spend like an extra in terms of like album sales, you'd never spend an extra £1 to get only 0.087 of an extra sale of an album. That would be a really bad idea. Well, unless you want to go bankrupt, then it's a great idea. What about for plays on radio? This had a rather larger value. So this is telling us that each time extra, so every additional time the song gets played per week on Radio 1, its sales increased by 3,589 units. Now that seems like I don't know, you might have to bribe the DJs. I really don't know how Radio 1 works these days. But there's probably some bribery and corruption goes on. But if this was actually like a financially cost-free thing, like maybe you just had to... Chris Boyles has left. I don't even know who does the Radio 1 breakfast show anymore. Who does it? Who? Oh, I don't even know who that is. Anyway, you might have to tickle them or something. But if it was cost-free, then this is a great thing to do. You get it played an extra time on radio, you get 3,500 extra sales. Fantastic. So that's your regular betas. Your standardized betas, like I said, are expressed in standard deviation units, which is as tedious as it sounds. So what this is saying, so for advertising budget, it's about a half. So what this means is that as advertising increases by one standard deviation, whatever that may be, record sales increase by about half of a standard deviation. So we'll look at this in the next slide, but in order to interpret this, we kind of have to know what the standard deviations of each variable are. But essentially, this is just a standardized measure of the strength of relationship. And actually, that is quite a strong relationship. So standardized betas can vary. It's a bit like a correlation coefficient. Because it's standardized, they vary between 0 and 1, hypothetically anyway. So if this was 0, that would be like no relationship at all. If it was 1, that would be like a perfect predictor. And this is about halfway between, which is actually a reasonably strong effect. Which again shows us that you can have a strong predictor or a strong effect that in real life has very little practical utility. So advertising budget is actually a reasonably strong predictor, but in the real world you'd never sort of spend lots of money to get so few extra sales. Now if we look at plays on radio, the standardized beta is about the same. It's about a half. So what this tells us is, statistically speaking, the strength of these predictors is about the same. It's about a half each time. So again, this tells us that if we increase the number of plays on radio by one standard deviation, sales of albums will increase by, again, about half a standard deviation. So if we were going to sort of compare which is, statistically speaking, the strongest predictor, there's nothing between them. They're both about as strong as each other. But again, I'm coming back to this point that you can have predictors that are, equivalent statistically, but in terms of their real-world utility, they can be very different. And as I keep saying, in this case, I think if you were trying to increase sales, you'd spend your time trying to get it played on radio and probably not be pumping money into advertising it. Just to make these standardized betas really concrete, you don't ever in real life probably go and do this sort of thing. You would just interpret them as they are. But just to make it very clear what they represent, here are the standard deviations of the three variables. So this is our outcome, sales. That has a standard deviation of about 80,000. Advertising budget has a standard deviation of about 500,000. And standard deviation of radio play is 12. So what we're saying with these standardized betas is that with advertising, as it goes up by one standard deviation, in other words, as it goes up by this amount, how many sales will we get? And because the standardized beta was about 0.5, it'd be about half this value. Similarly, the standardized beta for radio play was about the same. It was about a half. So this tells us if we get it played 12 extra times, so one standard deviation on radio, then again we'd expect about half this number of sales, which is what this slide is about to tell us. So if we increase advertising by a standard deviation, which turns out to be about £500,000, our record sales increased by half a standard deviation, so about 42,000 sales. This is just really, it's different ways of looking at the same things, sort of. And radio play gives us about the same number of extra sales, but from 12 plays on radio. So, our sort of normal betas, our parameter estimates, if you like, are expressed in the units that the variables are measured in. So we can't really compare them directly. Well, we can't compare them directly at all, actually. But they still tell us about the strength of relationship between predictor and outcome. The standardized betas tell us the same information, but in a standard way, which means we can directly compare how big they are in different predictors. So we can know statistically which predictor is stronger than the others without having to worry about how they're measured. Well, what units they're measured in, I should say. Okay, so we turn our attention to bias now, and I mentioned earlier on, so we're going to look at different things that might bias the model. And one of the sort of simplest things that bias a model is how you specify it in the first place. So you can specify models in a number of different ways. And in the output I put up earlier on, I said, well, there's two models, and I don't know what else I said because it was 10 minutes ago and I've got no memory. But anyway, we can fit models in different ways. If we've got more than one predictor, so obviously if you've just got one predictor, there's only one way to do things. You just put the predictor in and Bob's your uncle. If you've got several predictors, you can choose several different ways to start fitting the model. So one of them is known as hierarchical regression. And what this is basically that as an experimenter or researcher, you make informed decisions based on theory about which order to place predictors into the model. So you might put in what you know theoretically is the best predictor first, and then you start adding in other predictors later on. So you sort of build the model up hierarchically, step by step, adding in one or two predictors at a time. In SPSS, this tends to be called blockwise entry, because it terms things as blocks, but hierarchical regression. This, in a way, as I'll explain in a minute, is kind of the best way to do it. If you've got theory on which to base the order in which you put in predictors, then you should use that theory. That's definitely a good way forward. Another way to do it is the rather unpleasantly termed forced entry. So this is kind of like burgling a house. And you get all your predictors that you've measured, and you literally bung them in. You just say, I'll just throw them in all at the same time, see what happens. The final way you can do it is what's known as stepwise. So this is where SPSS decides which order to place the variables into the model based on a statistical criterion, which happens to be the semi-partial correlation, but that doesn't particularly matter. All that you really need to know is that it puts in predictors based on how good they are at predicting the outcome, essentially. So it will start off putting in the best predictor based on based on the correlation to begin with. Then once that's in, it looks around the other predictors and says, well, which one of these can add something to the model, can add a significant benefit to the model, and it throws it in. And then it looks around at what's left over and it says, well, can any other variables go in that will make the model better? So you're building the model up using statistics, essentially, which is not always a good idea. So SPSS will just be going around saying, right, we'll put the best predictor in first, then it looks around at what's left. Can we put something else in that will improve things? Yes, we can. Is there anything else that will improve things? Yes, there is, and so on and so forth. Okay. Hierarchical is generally a good idea because you're making the decisions and you're a human and you've got a brain and you can make these decisions in an informed and educated way. Forced entry is not necessarily so good. There can be uses for it, but one of the problems with it is, it's like making a cake and just bunging everything into the bowl at the same time. For some cakes, that will be fine, and you'll get, fairly nice results. But for others, it'll be a disaster. It won't rise in the oven, and it'll be horrible, and Christmas will be ruined. Your family will never speak to you again. And stepwise, because it's based on statistical decisions, that can be okay if you've got no other way of deciding which order to put things in. But it can also be a bad idea because there may be just very, very tiny differences between two predictors. One of them is a slightly better predictor than the other. It gets entered first, and then because it's been entered first, that affects what other variables get entered. So I've got hopefully a good analogy for this. So if you imagine I'm getting dressed in the morning. It's not the most pleasant image, I'll give you that, but it's quite useful. So I have a jacket, for example. Imagine this jacket is a predictor variable. I've got a waistcoat as well. Don't worry, this isn't going too far. So that's another predictor variable. So we've got two potential predictor variables. I've got shoes. Quite elaborate shoes. They're predictor variables too. I've got socks. Also predictor variables. So we go there. So we've got predictors. And because I don't actually want to strip in front of you, we've got pants and a t-shirt. So imagine I'm getting up in the morning and I want to dress myself. So I've got these predictors. I can choose any one of these to adorn upon myself. So I'm the model, if you like, and we're going to use these predictors to make me ready for the world. So we could do it hierarchically, so therefore I'm making the decisions. So I will look at my predictors and I will think, well, theoretically, it makes sense to put my socks on. So, I might put a sock on. And then I'll go, well, theoretically, now my socks in the model. Now my socks in the model, it makes sense, theoretically, to put my shoe on. Oh, yeah, thanks. Makes sense to put my shoe on. I've already put my pants on, obviously. So then I might say, well, put my waistcoat on next. So I'm making informed decisions about which predictors go into the model in which order. And the consequence is, I end up coming to work, hopefully, looking vaguely respectable. Now, let's imagine that I let a stepwise regression dress me in the morning. So my stepwise regression is going to make the decisions about which predictors go into the model. So what SPSS does is it looks around at my predictors and it says, what's the best predictor? Well, it goes, oh, it's your trousers. We'll put your trousers on first. So it puts my trousers on. Then it says, what's a good predictor after that? Shoes. Shoes are really good predictors. Let's put a shoe on. That's going to improve the fit of the model. So it puts my shoe on. And then it looks around and says, oh, these shoes don't go on. It says, what's left over? Oh, there's a sock. That's going to improve the fit of the model. Let's try and put that in. And then it says, well, hang on, these pants, they could improve the model. They need to go on too. Then it says, well, hang on, we've got a jacket here. That's going to improve the fit of the model. That goes in next. Oh, hang on, t-shirt. That can improve the model. We'll stick that on. We've got a fantastic model now. Fits the data really, really well. Basically, this is what happens if you do a stepwise regression. You end up looking like a twat. You're more of a twat than normal. So by letting SPSS make the decisions for you, you end up with socks over your shoes, t-shirts over your jacket, kind of weird Superman look in your pant arrangement, because it's making decisions based on statistics, not on sort of sensible information. So maybe there's only a really small difference between whether my t-shirt was a good, a good new predictor to put in, or whether my jacket was a good new predictor to go in. And all SPSS does is it just looks at the numbers. It doesn't look at it and go, no, it's stupid to put a sock on before your shoe. That's a ridiculous thing to do. It just goes, well, shoe's a good predictor. We'll bung it in. See what happens. And once it's in, it affects all the other decisions that SPSS makes. So, stepwise regression is not always a great idea because the decision making is out of your hands, and you're leaving SPSS to do stuff for you, to make decisions for you, and it's going to do them without any knowledge whatsoever of what's theoretically meaningful. So that's the first way that you can get bias into your model. The way that you select predictors affects the parameter estimates that you get. So you can have the same set of variables that you've measured, same set of predictors. If you put them in hierarchically, you'll get slightly different answers to if you put them in stepwise, and you'll get slightly different answers to if you put them in forced entry. So, think about your method. That's the moral of that story. We can also look at how well models fit the data. So we've already covered this a bit. So we looked at F, which is a sort of overall measure of whether the model has improved our ability to predict the outcome. We also had a look at R square, which tells us the sort of proportion of variability in our outcome that can be explained by the predictors that we've got or by the model as a whole. They're both very, very useful things. But we can also look at other things. So we can look at what are known as residuals. And you may remember from earlier in the course, residuals are just the errors you get between what the model predicts and the data points that you've observed. And we tend to do this, well, you can look at residuals in lots and lots of different ways. But I'm going to focus on what are known as standardized residuals, because again, they're like z-scores. So they're in a standard unit of measurement. So we can make some general rules about what they should or shouldn't be. We can also look at whether there are individual cases. So this is like outliers. When we talked about outliers before, this is kind of what we're doing here. So looking at cases that are influential, that have affected the beta parameters, have affected the model. So, just to remind you, like I said, these residuals or errors are just distances between the data we observe and what the model's predicting. So the green area is what the model's predicting, and the yellow dots are what we actually observed in the data. So we get these errors. You always get them. It's not too much to worry about, but we need to know that the errors are sort of there's not too many of them. So we can look at these standardized residuals. Like I said, they're basically z-scores. And we know a few things about z-scores. And one of the things we know is that 95% of z-scores ought to lie between plus and minus 2. It's actually 1.96, but 2 is easiest to remember. So what we can do is look at all the residuals for all the cases of data that we have, and we can just sort of count up, are roughly 95% of them falling between plus or minus 2? And if they are, that means the error is kind of what we would expect in a sort of normal sample. And you can go to a sort of more extreme level and say, well, we also know that for z-scores, 99% of them should fall between about plus or minus 2.5. Again, I think it's 2.58, something like that. But 2.5 will do. So if 99% of your errors or residuals are falling between those values, then that's fine. That's what you'd expect. But if you've got a lot more than 1% falling outside of plus or minus 2.5, then that means you've got a lot of residuals that are kind of slightly too big, or you've got too many that are big. And you can also look for individual cases that have huge standardized residuals. So if an individual case has a residual or standardized residual of above about 3, then that might be something you have a look at and see if there's a good reason why. Looking at residuals in itself is not enough, though, although it's useful, because you can have cases that in themselves do not have big standardized residuals. They don't have much error associated with them, but the reason they don't have much error is because they've had a massive impact on the model. So here's an example of some real data which measured the number of pubs in certain districts within London and mortality rates. And basically, this is the model that you get. So these all represent, a district of London is a dot, and number of pubs, number of deaths. So what you can see is you get this beautiful straight line like this, and then you get this massive outlier. And this outlier is actually the City of London, so the central bit of London, where there's an enormous number of pubs because it's the business centre. But relatively speaking, the mortality rate's not that high, well, not particularly high in central London relative to the rest of it. So it's a massive outlier in terms of how many pubs there are. It's not a particular outlier in terms of mortality rates. It's pretty, similar values to these. But what it does do is it has a massive effect on the model. So this is the model you get. If you fit a linear model to these data, that's the line you get. Now you can see that line is a really good predictor of that data point. There's very little difference between the dot and the line. It's so different, so little that you can sort of barely detect it, really. Whereas these values, for example, would have, not necessarily big residuals, but they would have some residual. There'd be some error associated with them. What happens if we get rid of that data point, if we fit the model without it? Basically, you get a completely different line. So by having this data point in the data set, this grey line kind of gets shifted, the whole angle, the intercept, everything. This has a massive, massive influence on what the model looks like. So this is what's known as an influential case, and influential cases are not necessarily outliers as such. So if you looked at the standardized residual, you would not conclude that was an outlier. You'd say, that's fine, it doesn't have much error attached to it. But the reason for that is because it's so much of an outlier, if you like, that it's actually influenced the model. It's changed the whole shape of the model that you've fitted. So residuals are not enough, because you can get cases like this, which if you just looked at the residuals, you'd think, they're completely fine, and actually, they're not. So what you can do is, again, SPSS does various things, and, there's a really tedious array of statistics that you can use to look for influence. At a very simple level, what you could do is fit the model with the data point in. So look at the green. Just looking at my dot. Look at the sort of reddish line, and work out or estimate the beta parameters for it. So you'd have a beta for the constant and a beta for the slope, and then you delete that point, and then you work out the new regression line, the beta 0 and the beta for the slope, and you compare the two. So you look at the difference between the parameter estimates, the difference between the betas, when you include the data point and when you don't. And if there's a big difference, then that's essentially a measure of influence. Now, obviously, you don't do that manually. SPSS can do all this for you. So you can look at that sort of difference between beta values when you have a case included and you don't have a case included is known as DF beta in SPSS. But I generally just stick to telling you about Cook's distance. And Cook's distance works on that principle. But what it does is, with the DF betas, you're getting the influence on individual betas in the model one by one. So you can end up with, about, if you had 3 predictors, you'd end up with 3 DF betas and a DF beta for the constant, whereas Cook's distance sort of wraps it all up into a single value, which is kind of convenient from a teaching point of view. So what Cook's distance does is it does this sort of comparing the model with a data point included against when the data point's not included, but it wraps it up into a single value. And as a general rule of thumb, if that value, when you ignore the plus or minus sign, if that value is greater than 1, then that's a data point that you should look at as possibly being an influential case, or too influential. So that's a nice, easy sort of algorithm to remember Cook's distance. If you ignore the plus or minus and it's greater than 1, that's potentially a problem. What about other sources of bias? Well, a few weeks ago we had a whole lecture on bias, and I'm going to return to some of those ideas now. So we talked about outliers, and we kind of just talked about them again, so I'm not really going to go on about that again. There was an assumption of linearity and additivity, which again I'm not going to talk about again particularly, but I just want to remind you that if we want to assess bias in a linear model, we have to assess whether a linear relationship is the best way to model the relationship between the variables that we have. What I am going to focus a little bit on is, you may remember there was an assumption about normally distributed something or others, and I'm going to come back to this in a minute. But essentially, if we're doing significance tests and confidence intervals around our betas, then it's the sampling distribution of those betas that needs to be normal. And if it's if we want the estimates of the betas to be optimal, then the residuals or the errors have to be normally distributed too. The other assumption we looked at was homogeneity of variance. And in linear models, it tends to be called homoscedasticity. But these are the same things, really. But it tends to be called homogeneity of variance when you've got groups of scores. And it tends to be called homoscedasticity when you don't have groups of scores, you just have lots of continuous variables. But they're basically the same thing. So we're going to come back to that as well. So this is just sort of flagging that we've talked about these things before. There's a couple of other things that we haven't talked about before, none of which take a lot of time to explain. They're all quite simple. First of all, we need to think about variable types a bit. So when we fit linear models, our outcome ought to be a continuous score. So you can fit linear models where the outcome is categorical or something, but those models are more complicated and we don't cover them on this module. The predictors in a model, they can be continuous, and generally most of the examples we've dealt with so far have had continuous predictors, like advertising budget that just ranges continuously on a scale. But it is possible to have categorical predictors as well, and that's what I'm going to talk about in next week's lecture. You'll find some textbooks talk about there needing to be non-zero variance, and that's really stating the obvious. It's just saying if you're going to put a predictor in, you have to make sure your scores sort of vary to some degree or another. Independence, the scores you get, or in particular actually it's the errors that matter, so again these residuals, they should be uncorrelated with each other. So in other words, there shouldn't be like a systematic pattern between them. The best way normally to make sure this happens is to collect data from different people, but you can still sometimes get correlated errors. So this is a bit important, but it's quite easy to check. And the other one is multicollinearity, and this basically just means that predictors in your model shouldn't be very, very highly correlated with each other. And that's really for obvious reasons. If you put two variables into a model and they're both very similar to each other, and they both correlate very highly with each other, then it becomes very difficult to estimate the betas for them because they're both kind of similar. So my slightly dubious analogy for this is if you if you went on a date with a twin or something, and like both twins were there and they were identical twins, that's important. It would be quite hard for you to be able to distinguish which one was the significant one to you. It's important it's a first date because obviously if you knew them a bit better, you'd be able to distinguish them. Although I do actually know some male twins who I haven't dated, and even though I can tell them apart really easily, I still call them by the wrong name all the time, which I think annoys them quite a lot. I don't do it on purpose though. In fact, I was even having a conversation with them once where I was saying, I don't understand why people can't tell you apart. It's really, really easy, and then called him by the wrong name. Anyway, so multicollinearity, it's like if your predictors are too similar, you just can't distinguish between the two of them. So when SPSS is trying to estimate the betas for you, it runs into trouble. So you want to try to avoid that. So, on a musical theme, I've written a little song to help you remember why normality and when normality is important. And I wrote this in the shower yesterday, so this is like a world premiere. So depending on your reaction, I may or may not use it again next year. And it goes like this. If SPSS says your data's a mess and you're going as mad as a hatter, 'cause you really want P to reflect reality, that's when normality matters. When you've been up for days in a statistical haze, you're tired and emotionally shattered. You don't want to be fooled by your confidence intervals. That's when normality matters. If your life has got skew and you're wondering what to do because you feel like your brain has been battered. If your samples are small, then remember the rule. That's when normality matters. If the scores you collect are distributional wrecks, remember that this doesn't matter. Because for CIs and Ps you need normality of the sampling distribution of the parameter. Thanks. It'll be on iTunes tomorrow. So normality matters, not within the scores themselves, but that's typically what we test. But it matters if we do significance testing. That's when it's important. If you want to trust your confidence intervals and trust your p-value, then it's the sampling distribution of the betas that matters. I feel like I'm singing again. And that is more important in small samples because the central limit theorem, which I couldn't fit into the song for some peculiar reason, the central limit theorem tells us in big samples that sampling distribution ought to be normal anyway. But we do need to look at the residuals as well. The residuals are important, at least in telling us that the estimates that we have are optimal using the method of least squares. So SPSS will chug out a nice distribution for you, a nice histogram and a PP plot. And you might remember from the lecture on bias, this PP plot, we want our dots to basically fit along that diagonal, which in this is actually the album sales data. So that's fairly beautifully normal, and you can see from the histogram that's pretty normal too. So this would be a situation where, happy days and all. If we saw this at the bottom of our SPSS output, we would look like this. We turned into an apple for some reason. But anyway, so we look like that. If, however, we see something like this, so this is, you can see quite a skewed distribution, and the PP plot, the dots are starting to deviate and S around the diagonal, so they're deviating a bit from normal, then that means that your betas have not been, the values that you have are not optimal. So maybe the method of least squares wasn't the best one to use, although that's the only one we teach you, but there you go. So if we see something like this, then look like that. Sad, sad, sad face. So, what about heteroscedasticity? I've got a song for that as well, but this is not a world premiere. And it goes like this. Heteroscedasticity is hard to say. If you get it, you'll hope that it goes away. Or perhaps that's syphilis, it's hard to tell. But syphilis won't leave you in statistics hell. If your residuals are funneling out, you better get ready to scream and shout. Because if your data are heteroscedastic, your model is a lousy fit. Genius. So, the important bit of this is not the like in your exam. Don't write anything about syphilis. That not good. Is that bit? So residuals funneling out. We talked about this very very briefly, and I said I would come back to it. And I put this diagram up before. So this is a plot of the Z-resid is your standardized residuals, which I've already talked about. And your Z-pred are standardized predicted values. So this is the values that the model predicts, but they've been converted to Z-scores. There's a lot of converting to Z-scores this week. So what we're hoping to see when we look at this plot of Z-resid versus Z-pred is this. Basically, a pretty random array of dots. If it's a random array of dots, that means, first of all, our residuals are independent, that ticks the box of independent residuals. If they're sort of all reasonably evenly spaced out, that means we've got homoscedasticity, which is a good thing. So that's kind of what we're looking for, really. And also, if it's sort of a fairly random, evenly spaced out pattern, we can normally assume linearity as well. So all good. So if you see something like that, very, very, very happy. If we have heteroscedasticity, that will show up as your residuals funneling out. So that's what the song was about. So you're looking for this sort of characteristic sort of funnel shape. And it may not be this way round. You might get, the funneling might go that way. That's fine too. But it's basically just, at somewhere along the x-axis, you've got a smaller range of your errors have a smaller sort of variance or smaller range than they do at the other end. So you're looking for it being wider at one end than it is at the other end. And that will show that's a sign of heteroscedasticity. Nonlinearity will show up on this plot if you get a sort of sausage shape. So this thing down here, that would be classic sort of nonlinearity. So like I said, if it's sort of fairly evenly spaced out, that means you can probably assume linearity. But if you get this something sausagey, and again, it won't look exactly like that sausage, but it will have some kind of bend in it somewhere. And this is an example where, literally, your model really ought to just give up the ghost. This is where you've got heteroscedasticity and nonlinearity at the same time. So you can see, like at this end, the errors are very, very widely spaced out, but at the other end, they're very narrow. So that's the heteroscedasticity. You've got narrow, wide. But the nonlinearity is coming out in that you've got a bit of a sausage thing going on as well. So if you compare these two, you've just got heteroscedasticity, and this is where you've got heteroscedasticity and also a bit of a sausage in there as well. So there you go. So these assumptions are, in a way, very easy to test. You just look at the graphs and you sort of make a call about it. And normally, heteroscedasticity is normally quite obvious, actually. It's not too subtle. Normally, if you have it, you've got quite a clear funnel. So what do we get for our actual album sales data? Up here, this is our Z-pred versus Z-resid, and we have actually got quite a nice pattern. There's no real obvious funneling, so we're probably all right as far as homoscedasticity goes. And it looks like a nice random jumble. That's exactly the sort of thing that we're looking for. Happy days. I've also put up here, you get out of SPSS these things called partial plots. So this is a plot of each predictor. So this is advertising budget, that's plays on radio. And actually this was I had another predictor, which was the attractiveness of the band. And I included this just because you get to see some funneling. So you can also look, if you want to see like which variable is creating the problem, these partial plots are useful. So you can see here basically a nice linear trend for advertising budget. So that's kind of happy days, and the spread of scores is reasonably even along the whole length of advertising budget. Again, this shows a sort of a nice linear pattern as well. So these two predictors, kind of pretty much okay. The spread around the line is reasonably even. It's not too bad. Like I said, I sort of threw this into the mix just because you can hopefully see that there is some funneling going on. So if we'd looked at a model with this in as well, that might be a reason to think about not including that predictor. So multicollinearity, which is the last thing we need to worry about, again, it's quite easy to check because SPSS throws out some statistics. So if you'll see how to do this in your practical class, but if you basically tick on a box, like look, there's a little checkbox that will give you these two columns as part of your output. And what you're looking for here is tolerance and VIF are actually the same thing. So basically, that's an interesting thing to remember. So tolerance is 1 divided by the VIF, and VIF is 1 divided by tolerance. So they're completely related statistics. I don't really know why it gives you both of them, but anyway. There are some interestingly contradictory recommendations about tolerance. So Maynard said that tolerance should be more than 0.2. So in this case, all our tolerances are bigger than 0.2, so that shows no multicollinearity. That's good. I find this easier to remember because it's a nice kind of round number, is the VIF should be less than 10. So you'd just be looking down this column. If there's any values here greater than 10, then that potentially shows multicollinearity. So that's a problem. These are all smaller than 10, so based on this criterion, no problem at all. So just to summarize all of this, once you've fitted a model, we need to assess its accuracy, we need to look for sources of bias, we need to get some idea of, is it actually a decent fit, or are there things affecting it? We can look at how well the model fits the sample. We could do this by looking at residuals, influential cases. We would need, in the first place, to think about which order we put predictors into the model and whether we do it stepwise or hierarchically. And there's also the issue of kind of how well the model sort of fits the population, really. And that's when we start talking about confidence intervals, that's what we're doing, really. We're trying to estimate what the actual value of betas are in the population. We've seen that normality matters for significance tests and confidence intervals, but also the normality of residuals, which we haven't talked about as much before today, matters in terms of knowing that the betas that we've got are sort of optimal using the method that we've used. We need to look for homoscedasticity, look for to try and make sure that there is actually linear relationships between the things that we're modelling, and also look to check that our residuals are independent. So next week is the final lecture in this sort of segment, which is going to look at categorical predictors. And that's it. Thank you.